Okay, so we finished our study of geodesics and geodesic congruences for now. There's a lot more to say about that subject and it will come. But the idea that's been communicated so far is that there is space-time. We can think of space-time in terms of its points and its geometry, its metric. But that alone doesn't give us enough insights. There are also insights to be gained by talking about geodesics and families of them and filling the whole space-time or at least an open set with geodesics and trying to see what equations they satisfy. And it turned out quite complicated, and we also hopefully learned that the null case has its own different complications from the time-like case, and that pretty much everything in GR needs to be you need to be prepared at any time to know whether you are discussing the null case or the time-like case, because they have different flavors. Now we are going to very rapidly, so I talked to Omkar today and he said he's already done maximally symmetric spacetimes in the first course. Not all of you have had that course, but anyway, it won't kill us to do them again a little faster, and maybe with some things you might actually not have seen. So my plan for today, of which I've already wasted 15 minutes of both of us, is to talk about Minkowski spacetime in as many different ways as possible. So, of course, it has a well-known metric minus dt squared plus dx vector squared. This can also be written as minus dt squared plus dr squared plus r squared d omega d minus 2 squared. So here's another context in which you see d minus 2 coordinates singled out from the total of d, and what is not in those is one space-like and one time-like coordinate. And we know already that these two are going to create between them two null directions, and so it's something that actually is potentially interesting. The isometries of Minkowski are of course known. So there's translations, constant translations, and then there is Lorentz transformations. So instead of writing delta x mu, I'll write the killing vector. So this is nicer. And these are, omega is an antisymmetric matrix when both its indices are lowered, and this contains Lorentz as well as rotations. And this of course is translations. And if you add up the number, you get capital D, D plus 1 by 2. So it's maximally symmetric, and the symmetry group is called ISO D minus 1, comma 1. SO D minus 1, comma 1 was just this, and the I refers to the fact that there are also translations. Good. Okay. Now, this is all very well, but we want to look at different coordinate systems in Minkowski, for Minkowski spacetime, which give us different insights. And one thing we can do is to start with, so take minus dt squared plus dx squared and write it as, single out the last space coordinate. Again, we leave d minus 2 of them, and we take the combinations u equals t minus x d plus d minus 1, and b is t plus x d minus 1, and this goes by the name of a retarded coordinate. and this goes by the name of advanced. And one of these is also called, they're also called ingoing or outgoing. So the idea is that u equals constant is the trajectory of a light ray, because it means t has to be equal to xd minus 1. That means that the velocity is 1, which is the velocity of light. And moreover, x is then increasing with increasing t. So this is outgoing. And v equals constant is ingoing. And as always, our convention will be that it's the sign of the space coordinate which changes between outgoing and ingoing, so that the time coordinate always contributes a positive amount. So if I am at a fixed place, then t will always increase, of course, because we can't stop it, and then u and v will both increase.
Why it is retarded?
Why it is retarded? I guess because we have, so t was the original time, and now it's an earlier time, earlier by the amount of space. But of course xd minus 1 can take either sign. Maybe it's the, I don't know. The point is t and xd minus 1 both can take either sign, and you can also exchange them. So I don't know, it's just called retarded.
From electrodynamics.
Yeah. But why specifically the choice? Can you tell me which is the right, I mean, why, which choice, why did I call that retarded and not that one advanced?
Yes, so you first do this in spherical coordinates where it is t minus r and
Yeah.
t plus r, and
Yeah.
r is always positive.
R is always positive. Good. So in that case, if R is, yeah, we are going to do that in a moment. We are going to do that very soon. Okay. Anyway, the point is that now, so this is one way we can make the metric. And of course, with this choice, the metric is minus du dv plus dxa dxa. And this is like the very standard null. So this is where, so u and v are both null. And null simply means there's no du squared and there's no dv squared term in the metric. So that's straightforward. Now, the alternate which was just mentioned was to not start with the Cartesian coordinates, but instead start with the spherical polar coordinates, and now take the null combinations. So we'll give them the same name, but this is a very different coordinate from those. And actually I should have not used these words here, because this really would, the correct meaning of u equals constant was positive going, if you like, right going. If xd minus 1 is the horizontal axis, then the first one is constant, v equals constant is right going, and v equals constant is left going. But here it is really outgoing and ingoing. So this is the place where these words are correctly applied. Now you may wonder what nonsense I am talking, because we are in Minkowski space-time, which is empty, and there isn't anywhere to go in or out from. And the reason is that we have simply made an arbitrary choice of spherical polar coordinates, and we are doing everything with that. And spherical polar coordinates have this property that there is a center, and there may or may not be something at that center. It's a choice of coordinates centered somewhere. They are useful if there's a spherical object which is centered there. I mean, you could, in principle, consider a sphere and define spherical polar coordinates with their center somewhere else, but you would just make your equations horrible for no reason. The whole idea is to pick a system which is spherically symmetric and put the origin of polar coordinates there. Here the system is very symmetric. It's spherically symmetric about any point because it's empty. But we are just doing this as an exercise. We won't learn anything very deep with it, but we'll realize that there are different types of coordinates you can think about. And if you then start studying actual spherical systems like the Schwarzschild metric, then you'll immediately realize that all of these coordinate choices have some analog there, and each of them can teach you something different about the space-time. Great thing about GR is that there's no best coordinate choice for any problem. There are many different, and usually in each of them we learn something different about the space-time. Now in this case, the metric is just again du dv minus, but the other term is a little more complicated. Okay, and here there's a constraint which was not there before. Since r is positive, v is always greater than u, because v minus u is twice r. So we have v greater than or equal to u, if you like, and with equality only when r is 0. Okay, good. Now, something that people find surprising the first time they see it. Suppose we choose the same spherical coordinate metric which is at the top there, and we define u equals t minus r, but we don't define v. There's no coordinate v. We simply keep r. So u is t minus r, and we also have r, and of course we always have the angles of that d omega d minus 2. Okay. Now something quite unexpected happens. Maybe all of you have seen it, but it's a bit startling when you see it for the first time. The metric becomes this. And what you see is that there is no dr squared. So r is a null coordinate. And why it's startling is that we never redefined r. R was there from the beginning. What we redefined only was t minus r is u, but u is not a null coordinate. There is a du squared term, but there's no dr squared term. So that's quite remarkable. And these are what are called Eddington-Finkelstein coordinates, and I think these are the ingoing Eddington-Finkelstein. Similarly, or we could define v equals t plus r, and then keep r and theta a, and again r will be a null coordinate, but now the metric will have a v in it. So there's a similar thing. It will have plus, in this case it will have plus dv dr plus etc. Of course, all these metrics can be changed by scaling various things. Okay, so these are called, so let me see, this so the first one is called outgoing. Hopefully that's what we said, yes. So this one is called outgoing Eddington Finkelstein coordinates. Again, I emphasize Eddington and Finkelstein. I don't think we're trying to just find new coordinates of Minkowski space-time. They were actually trying to study a more complicated problem, namely the Schwarzschild solution. But the coordinates exist even for Minkowski, and you can, once you realize the cute property of this, then you can make it work for you in an actual spherical symmetric non-trivial space-time. Okay, so that was very quick. Now that's very simple also. Now let's move to a more interesting coordinate system for Minkowski space-time, and these are called the Rindler coordinates. Are there any questions about what I did so far? Good. Okay. So let's start with the standard coordinates. Again, so there are two approaches to this. One is to start with this, consider the behavior of an accelerated observer, and then choose coordinates which are adapted to that observer, and you end up with Rindler. So they are the coordinates appropriate for an accelerated observer in Minkowski space-time, and very surprising things happen. You could do the opposite, which is what Wald does, which is to introduce the Rindler metric and then say, what is this metric? It looks singular, very interesting, strange, it's only valid in some region, something, and then can we find a way to remove the coordinate singularity, and then study its geodesics and realize that there's a nice coordinate transformation and end up showing that it's actually Minkowski space. So you can start with a non-trivial metric and realize that it's Minkowski, or you can start with Minkowski and construct that metric. Good. So now let's consider a particle which has a trajectory x mu of tau, but I won't insist that it's geodesic. In fact, it's not going to be. Still, the velocity vector of this I can still write as u mu, and the velocity vector will always satisfy this. And now, so now we are imagining a physical particle, and this relation actually comes from the mass shell condition, p squared is equal to minus m squared, and because of that constraint, the energy and all the components of momentum are not independent. And when you divide that relation by the mass of the particle, you realize that it is just a constraint on the d velocity, or the fall velocity, or in general d velocity. So now we really have in mind a massive particle of some mass which has scaled out of the problem, because this relation is true no matter what the mass, as long as that mass is non-zero. Okay. Good. So now we'll choose the velocity to be such that its components ua are 0 for a equals 1 up to d minus 2. So that only leaves two possible components, and so that relation says that minus u0 squared plus u d minus 2 squared is minus 1. Good. Now this is a hyperbola, so we can solve it by a standard parameterization. And so, do this again. So u naught will simply substitute it as cosh of some unknown function beta of tau, and u d minus 1 will be sinh of the same argument, and then of course that equation is simply true. It's simply true. Okay. Now let's talk of the acceleration. So the acceleration of this particle is something we've actually been discussing for several lectures, but not in this language. It's just this, and if you expand it out, it's the left-hand side of the geodesic equation. And the geodesic happens, it's affinely parameterized when the acceleration is 0. Okay, but now we don't want it to be 0. First thing we note is that we are not assuming there's any geodesic here. I mean, we're not working with a geodesic, we are working with an arbitrary smooth path, x mu of t, of tau, and we are in Minkowski space-time, so this covariant derivative is just the ordinary derivative. So this is d2 x mu d tau squared, which is the sensible thing to call the acceleration. Okay. Now let's calculate it in this parameterization. So I think then I just need to call it du by d tau. So, and let's give it a name. What have I called it? Alpha. So alpha 0 is equal to the derivative of that, which is beta dot sine hyperbolic beta, and alpha d minus 2 is beta dot cos hyperbolic beta. Beta is still an unknown function of tau, so it's a general situation. But now, what's the magnitude of alpha? Therefore, is equal to minus So it's equal to beta dot into square root of minus sine hyperbolic square beta plus cos square beta, and so it's just beta dot. And now we are going, up to here we haven't made any choices. We've just written something about the kinematics of a massive particle in Minkowski spacetime. And now we are going to make a choice. The acceleration is constant. So we are going to study the motion of a particle with constant acceleration. I won't put mod, I'll just call this number alpha, but it's defined to be square root of, it's defined to be exactly this. So the acceleration is constant. So beta dot is constant. So this implies that beta is equal to the constant acceleration times tau plus another constant, which is just additive and which is arbitrary. So I can just choose this constant to be 0. So this beta is linear. That's what we get for a constant acceleration. Okay. And therefore at the end of this process, which maybe many of you found completely trivial, we concluded that u naught is cos of alpha tau and u d minus 1 is sinh of alpha tau. Okay, good. Now, therefore, we can, now we have to integrate once more, because remember u mu was dx mu by d tau. One more integral will give us the actual trajectory. Again, we can choose our initial point and so on as we like. So x0 is finally going to be the number 1 by alpha. Alpha is the constant acceleration throughout, and sine hyperbolic alpha tau, and x d minus 1 is 1 by alpha cos alpha tau. Good. Now what's the invariant distance from the origin? So because of our choice of constants, which we have at various times set to 0, there is actually now a sort of origin. Okay, and so there is a sense in asking what is the invariant distance from the origin. But of course, at the same time, we know very well that in Minkowski space there is no origin; it's completely translation invariant. But we are treating an observer with a certain acceleration and with a certain trajectory. And so we can ask what is the invariant distance of this observer from the origin, and it is just x square root of x mu, and that is equal to square root of, so that is just, it's a trivial calculation, it's just 1 by alpha. So this observer, even though their coordinate distance is changing with respect to the origin, their invariant distance, again it's a quantity which you can talk about in Minkowski. Here we have used the Minkowski metric to create the square. This is just constant. So now we are going to take this to be a new space coordinate. So take so we are going to do a transformation x. So our original coordinates were small x, 0 and d minus 1. And now we are finally going to transform coordinates. Till now we didn't transform any coordinates, we just discussed the trajectory of an accelerated observer. Now we are going to actually write that the d minus 1 coordinate is written as capital X cos alpha t. You can see that t has been identified, the new time is the proper time, and the new x is the invariant distance. I think you can see it from this, because 1 by alpha is the invariant distance. So we just, from this equation, we have chosen, this equation is inspiring us to take coordinates where this is the position and this is the time. Good. And and so therefore x0 is, I keep looking at my notes because I can easily mix up the sine and cos otherwise. And it's kind of funny because so u mu is negative, but alpha mu is positive. The acceleration is a space-like vector. So every time you differentiate, the sign of that derivative magnitude changes. Okay, so this is an invertible transformation, at least in some range, and we'll talk about the range in a minute. But first, let's just write the inverse if it exists. And so that is x is given by square root of minus x. This is what we basically decided from the beginning. And tau and t is just given by, in terms of this, it's given by 1 over alpha tan hyperbolic inverse t by x t minus 1. So this is the functional inverse of that transformation. And the last thing now to do is to insert this into the Minkowski metric and find out what the new metric looks like. And so notice, by the way, that everything we are doing is for 1 plus 1D Minkowski spacetime, because all the other coordinates have just been set to 0. So this is a particle just moving along one line. And in xt space, the metric is minus alpha squared capital X squared dt squared plus dx. And there is always that d small x a squared, where those are d minus 2 extra directions, and we are just going to drop them. Now people drop this also because you can simply rescale the time to eat up this quantity. But it's nice to keep because dimensionally, so in relativity we normally take c equals 1, so x and t have length dimensions, but then this has 2 extra length dimensions. But then this, being the inverse acceleration, has inverse of length dimension. So alpha times x is dimensionless. So this gives you some idea of the scale of the acceleration. And now we can ask about the range of the coordinates. So we'll allow x and t, capital X and capital T, to range over anything. They are real numbers, so they can go from minus to plus infinity. But because of the transformation we made, we find that x d minus 1 plus x0 is equal to capital X e to the alpha t, which is positive. So, well, okay, I shouldn't say that in such a hurry. Give me a second. X is there, let me not say what it is because it does depend on it. And xd minus 1 minus x naught is equal to x e to the minus 1. So this factor is always positive for real t. Okay. So the end result is that xd minus 1 is greater than 0 and mod of x0 is less than xd minus 1. And so this is our original, what is going on? This is our original coordinate system, xd minus 1 and x0. And what we see is that we are simply in this region. So yes.
Did you take that xd minus 1 is greater than 0?
Yeah, good. So certainly if capital X is positive, that is true. I think
shouldn't the x naught also matter? Oh wait, if
no. So for example, if you can just add these two. If you add these two equations, you find xd minus 1 is capital X times cos So if capital X is positive, then X. So this is all for capital X positive. And actually there's a singularity at capital X equals 0. So I think we took capital X to be a square root. So we had chosen a sign, I forgot to say that. So let me say that here. Well, I'll put greater than or equal to. It's in the same sense that in polar coordinates we write r greater than or equal to 0, but we know that really it shouldn't be 0. So with this we get these bounds. So by adding this you find that first of all now both the right hand sides are positive. And by adding it you realize that xd minus 1 alone is positive, so I must be in the right half. But then because each of these is positive, you see that the magnitude of x0 has to be less than xd minus 1. And that confines me into this wedge. And you must have heard the term Rindler wedge. So this is it. Good. Okay. Now what is the actual trajectory of an accelerated particle with, of course in the Rindler wedge you can discuss all kind of trajectories, and you don't have to limit to the specific particles that motivated this coordinate system, but the particle with constant acceleration is one which comes in nearly at the speed of light, slows down, at this point it's at rest because it's vertical, so x is not changing, and then again starts to accelerate and moves in the opposite direction again at the speed of light. So its actual motion is, here's a point, the origin, it's coming in from positive xd minus 1, slowing down to rest here and then going back along the same axis. So that's constant acceleration. The constants we chose, integration constants, made this symmetric about this so that it really came in from minus infinity with a speed of roughly the speed of light, because it's almost touching this. What does light do? Of course, light goes along light cones. And basically that's it. So light corresponds to x d minus 1 equals x 0, and if I put that here I should find that capital X is 0 because look at the second line and first or second line there. So actually capital X is 0, but also if I divide the two lines I still find that the left side is either 0 or infinity, which means t must be infinite, either positive or negative infinity. So these light cones map to x being 0 and t being plus or minus infinity. So remember, x was the invariant distance from the origin, and with our choice of integration constants, light just passes through the origin, but the other massive particles, because of the acceleration, bounce back. And so clearly there's some singularity here at x equals 0. Okay. Now, staring at the Rindler, why have we done all this? Well, there are many reasons. Again, you know the words. It's going to turn out that Rindler space has a horizon, and it's a very mysterious fact because it's just Minkowski space under some other name. But the accelerated observer sees a horizon and then eventually will find a temperature for that horizon and a surface gravity. But we are not going to discuss any of that now. We just want to understand the kinematics of this, and then I have other things to discuss. So let's just stare at this metric. So one thing you can do with any metric is, if you see that the metric the coefficients of each of the terms in the metric don't depend on some coordinate, then that coordinate is a killing vector. That's the easiest way to find killing vectors. Actually, it's almost the only way people keep finding killing vectors. They just find a coordinate system in which some coordinate drops out from the metric and they say, okay, there's a killing vector. So this metric, Rindler metric, has a killing vector del by del tau, del by del t, because the metric doesn't depend on t. Whenever you have a time, and of course t suggests that it's time, and of course t, you can see from the metric that t is the time coordinate, it has that negative signature. So whenever you have a time-like killing vector, that's the time, natural choice of time in that metric. So Rindler metric is one where you think of t as being the physical time. But what is it with respect to the original metric, considering that the original metric had its own time? This is certainly not d by dx0, because we did a quite non-trivial transformation. And in fact, it's easy to see that what this is alpha, the inverse acceleration, times xd minus 1 del by del t plus t del by del xd minus 1. So what is this? This is the killing vector of the original Minkowski metric in the original coordinates, and what does it represent? Lorentz boost along xd minus 1. I'm sure most of you know this, but if there's a plus, then it's a boost, and you'll have one space, one time, one space. If it's a rotation, both will be space and there'll be a minus. That's the fact that the rotations form compact transformations, and the boosts are non-compact. Okay, good. So that's pretty much what I have to say about Rindler space. Good. Are there any questions?
So the Rindler's, to define a Rindler wave, we need a particle. We can't define it using the space time.
Well, you can just, it's a coordinate, the coordinate transformation you can define as you like. You don't need any particle to do that. If you look, any metric you can just write down out of the blue. You don't have to prove anything. For example, the metric which I wrote, minus x squared dt squared plus dx squared, you can calculate its Ricci tensor and you'll find it 0. So it's a valid solution of Einstein equations. And you might have, this is what I said, Wald's approach. You might never know where it came from or what it represents. It's just a metric. You can just study it as a metric, and it's a flat metric moreover. But the particle was introduced so that you get a physical understanding where the metric comes from relative to the original Minkowski spacetime. Because I have Minkowski, any coordinate transformation I make will leave me in Minkowski, because it's just new coordinates on that spacetime. Changing coordinates cannot give you a new space or spacetime. So we took new coordinates which were inspired by a particle which is uniformly accelerating, massive and uniformly accelerating, that's all. And basically that particle sits at constant value of x for all time. Time is always progressing. What we have done is to map that particle's trajectory onto a line, vertical line. So if I looked in Rindler, so we didn't draw the Rindler coordinates, but if I did, then this would be a particle with some acceleration, particle with acceleration 1 by x. If this point is x, let's call it x hat, then the acceleration is 1 by x hat. So if the particle is undergoing an acceleration which is larger and larger, it's coming in. Okay, so so the accelerating particle in Minkowski is a particle at rest in Rindler. That's the picture. And in this picture, weirdly, light also seems to be at rest, because light is x equals 0. But in fact, we see that when we take x to 0, t has to go to plus or minus infinity. So it's actually a singularity of the coordinate system. Otherwise, it would be a bit absurd if light was actually undergoing a trajectory like that at rest. It would be like having a description of light in special relativity where it's at rest. That shouldn't exist, and actually it doesn't because of the fact that t goes to plus and minus infinity. But for all other values of acceleration, t actually just takes all its possible values. Yes? And
can we make any comment when the acceleration is not constant?
is not constant? Yeah, of course, it will be different kinds of lines.
And there,
So you could have a increasing acceleration, and I suppose it would go something like that. Okay, and
in the Minkowski,
this is, see, these are Rindler coordinates.
Yeah.
The same trajectory will look different in Rindler coordinates from what it looked in the Minkowski normal, usual coordinates of Minkowski.
yeah. So my question is, this cone will become smaller.
Cone doesn't become anything. The particle is doing different things in this. First of all, this is the whole cone. The whole cone has been mapped onto this space. Sorry, x is so the right half of this space. Because we took a choice of square root in defining the acceleration. So we are either in the right half or the left half. Now there's actually a way to extend Rindler to all the parts of Minkowski, but still there are, those separations are important. Those actually will turn out to be horizons. Okay, but this is the cone in these coordinates is just the right half plane. Okay, and the particle which is accelerating less and less, this is going to go out. So a particle at rest in this picture is not drawable in a sense. It lives at x equals plus infinity. And then as its acceleration increases, it's like this, and it's vertical only if the acceleration is constant. If the acceleration is variable, for example, acceleration is linearly growing or decreasing, that means that the velocity was quadratic in t or something, then it will bend in various ways depending what. So all possible trajectories are allowed here, but the cone that never changes. That Rindler, the wedge in Minkowski space is where all things are possible in the Rindler coordinates. You can't go out of it. And actually the fact that you can't go out of it is the statement that there's a horizon. Yeah.
Yeah, so regarding the statement of horizons and
Yeah.
all, I am a bit unclear on that. So what I'm trying to understand is that, okay, a particle is coming, following that hyperbola.
Yeah.
And then according to the particle, it can't like go to the places beyond that, beyond the light. So
Yeah, of course, the point is that in Minkowski space, of course, the particle can go beyond that by just going.
This is just a mapping of the Minkowski space in different coordinates.
It's a mapping of part of Minkowski space. It only takes the Rindler wedge
Okay.
and maps it to this thing.
Okay.
So in a way, you might imagine there was a wedge, and you might imagine that by mapping I've expanded it or something and put it here.
Okay.
But now, in these coordinates, there's no way, or even within that wedge, there's no way to, in these coordinates, there's no way to go out of the wedge, because this is the allowed space of these coordinates, and we should think of it like an r and t, like a radial coordinate and a time, in the sense that this is also positive like a radial coordinate.
Yeah,
So then I can't go anywhere, I don't have any way to go anywhere.
Yeah, that I got it,
Yeah.
because that's what we are doing with the
Yeah.
coordinate transformation. But like physically, how did the observer in the Minkowski space get
Yeah.
restricted to this by acceleration?
Yeah.
And like if he stops accelerating,
Yeah,
then
the observer
will
is-
the Minkowski space appear again. So that's
Yeah, so we'll discuss all these things in due time. For this, we really need to define many things about causality and geodesically complete spacetimes and all sorts of things. But just the basic idea is that if you're accelerating uniformly, then you are restricted to the wedge because your trajectory is a hyperbola, and by changing the amount of your acceleration, you just make the hyperbola become more sharper or flatter, and that's it. And these are well-known things in Minkowski. But once we make the coordinate transformation, then we seem to find other things happening, and we find that this accelerated observer actually starts to see a horizon as well as a temperature associated to that. And okay, the point is that it is a manifestation of something we know, which Einstein said, which is gravity is acceleration. It's the same thing. There's no invariant way to separate what is gravity and what is acceleration. So that, but since gravity is supposed to lead to at a horizon leads to temperature, then acceleration and its horizon should also. But again, let's not prejudge all these things. Let's just try to understand this geometry for its own sake. So this is Rindler geometry. And I emphasize, people keep saying Rindler observer, that's simply the observer at rest in this geometry. Okay, but there can be other observers in this geometry. Good. Okay, then in the remaining time, 2 more questions. I'm going to discuss Penrose diagrams, and we are going to remain in Minkowski because the Penrose diagram has completely different features in different space times, and so to just introduce it, you have to have a particular space time in mind. So what's the idea? Physics at infinity is interesting. There are many reasons for that, one of which we already know from electromagnetism. If you want to understand what is Gauss' law, you need to enclose a system in a sphere, but conceptually we take this sphere to be very large, which encloses all charges in the system, so it's like sphere at infinity. So there's a way of thinking that a conserved charge is some integral over some sphere. Of course, you can have locally conserved, but the sphere at infinity is the thing that captures all the charge in your system. It's also true in gravity that the sphere at infinity captures all the mass in your system. This is through what is called the ADM formalism. So being at infinity is a nice thing. Moreover, here we are in space-times which are not necessarily flat. So the nature of their infinity itself can be quite non-trivial. You know already that the infinity of Minkowski doesn't look anything like the infinity of ADS or DS spacetimes. And broadly, these are the 3 types of behavior you can have at infinity, though you can also have discrete quotients and so on. So you can have a number of things happening at infinity, but infinity is very far away. This is one fact, but the other fact is that infinity is quite far away. So it's very hard to draw a diagram. To be precise, it's infinitely far away. So it's hard to draw a diagram where you can actually assess what is happening at infinity or see infinity in front of you. And the trick is proposed by Penrose. Replace the physical metric of any given space-time by an unphysical metric as follows. You have a physical metric G mu nu of x. You multiply it by a scale factor, and this is your unphysical metric. We are not doing anything to the coordinates. This is not a coordinate transformation. It's not a isometry transformation. It's not anything. It's just, this is a new metric. It's a different metric from that metric. If this metric solves some equations, it doesn't mean this metric will solve the same equations. Okay, just a auxiliary construction, if you like. And the trick here is that you choose, it's a very, very brilliant idea, choose the scale factor omega of x so that the metric, the unphysical metric, statement. Yeah, so that in the unphysical metric, infinity is brought to finite distance. And this sounds a bit strange, but it's as soon as we do it in one example, it will become clear what we need to do. Okay. Now you know that a local scale transformation is also called a conformal or a Weyl transformation. So this is sometimes called the conformal factor. It's really just a scale factor. And the resulting spacetime done by doing this, I've been calling it unphysical, but there's a more polite name for it. We'll call it conformally compactified. So it's a conformal compactification of the original spacetime. So G tilde mu nu is a conformal compactification of the original spacetime with metric G. Now, doing this kind of procedure may map some nice, useful physical metric into some rather unphysical metric, but it's not going to be much use if in this unphysical or compactified metric, every time you draw a line or you look at some trajectory, you have to undo the conformal transformation to see what's really happening. It will only be useful if it tells you some facts which are true in this new metric. And that happens because of the property of conformal transformations. Conformal, as you may know, means angle preserving. This is the angle between the angle at a point between two lines that cross at that point. And one implication is that light rays which were at 45 degrees before, so continue to be at 45 degrees. Plus minus 45 degrees. So if in the original Minkowski metric light rays went along light cones, they'll still go along light cones in the new coordinates. So causality, as a result, causality can be studied in the new metric. And that's the basic idea. So let's do it for Minkowski spacetime. The point though is, it's not easy to find this conformal transformation which brings infinity to a finite place, because I can just try to take the Minkowski metric and multiply by something. I'm not going to get any useful answer. So to actually use it, you have to first transform Minkowski to some other form, and then some factor will pop out, and then you have to basically remove that factor. So that's what we are going to do. So we are going to start with the form minus du dv plus this other stuff. And we are going to, so this is where you have two null coordinates, and we are going to define tan u tilde equals u and tan v tilde equals v. So the real trick is actually here, because tan, as you know, maps a finite range of angle minus pi by 2 to plus pi by 2 to an infinite real line. This is actually the step that's going to bring infinity in, and then we'll still have the point is then we still have to drop a prefactor to get the conformally compactified metric. So first let's implement this. First of all, because of this we find some restrictions on the coordinates. So with this, already v was greater than, okay, this was by the way done in the radial. Here u and v were t minus r. We're not doing it with singled out space coordinate, but with the radial coordinate. That's important. So because r is positive, v is always greater than or equal to u. So u was less than or equal to v, but now the tilde one is this. Satisfies these relations. And the interesting thing is that v tilde going to this value or u tilde going to this value are the points at infinity of my space, and I can't reach those points. I can only reach them as a limit. So right now v is just less than pi by 2 because remember the original coordinate u and v, I cannot give them the value infinity. I can just say that they are any large value, however large. And therefore, under this transformation, u tilde and v tilde I can get as close as you like to pi by 2 and minus pi by 2, but not touch it. Okay. And what is the metric? The metric is easily calculated to be sec squared u tilde, sec squared v tilde with a 4, and then minus t u tilde dv tilde by 4. No, 4 of minus 4 times. No, what am I doing? Oh, with a 1. 1/4. So this is minus 4 times and plus sine squared v tilde minus u tilde d omega d minus 2 squared. There. So you can see why we are not allowing u tilde and v tilde to touch these endpoints. If they do, this factor diverges. So the metric just isn't well behaved there. But now we have it in the form where we can apply Penrose's idea, and the idea is just delete this. We just multiply the metric by omega squared, which is exactly 1 upon this thing. So our conformal factor is twice cos u cos v tilde. And now we get a very different looking metric. So up to now this was entitled to be called ds squared because it's just the same Minkowski metric just in new coordinates. But now we are only going to write what's inside the bracket, minus 4 du tilde dv tilde plus sine squared v minus u d omega squared. And this is an altogether different metric. To understand this metric better, so now with this, first thing to note is nothing goes wrong if I send v or u to their endpoints, v going to pi by 2 or u going to minus pi by 2. And so I can now put the equality sign at the two ends. So for this metric, I think a purist might keep this sign as a strict inequality because, as I said, v equals u is when r is 0, which is a singular point of polar coordinates. But as long as we understand that, I think this is all right. And the act of putting the equal sign here and here is the conformal compactification because now the boundary is part of the spacetime. So that's the stage at which we did a conformal compactification. Okay, and now it just remains to draw what these coordinates cover. So now we define u tilde to be t, new coordinates t and r, but divided by 2 this time. The reason for dividing by 2 is that we want this sine squared of v minus u to become sine squared of r because that will give a standard metric. So with this now the conformally compactified spacetime is minus d t tilde squared plus d r tilde squared plus sine squared r tilde d omega d minus 2 squared. Now we find an interesting thing. This is the metric of a d minus 2 sphere, but if I multiply this with sine squared r tilde and add d r tilde squared, then it's a metric of a d minus 1 sphere. So this whole thing is the metric of a d minus 1 sphere. So my space-time is actually S d minus 1 cross R. By doing this conformal compactification, I've changed its topology from Rd to Sd minus 1 cross R. Okay. Now it only remains to plot the range of these T tilde and R tilde coordinates. The point is that if they were unlimited, that is R tilde was just anything positive and T was any real number, then this would be all of St minus 1 cross R, but it isn't, because we have the following restrictions. T tilde is bounded between minus pi and pi. R is bounded between 0, always 0 is in that sense, which I've mentioned a few times, and pi. And T minus R has to be greater than or equal to minus pi, and T plus R has to be less than or equal to pi. These are all the constraints we inherited from the constraints on U tilde and V tilde, which, if you remember, were arguments of a tan function. So as the true or the original coordinates ran over some infinite range, V tilde and U tilde got restricted. That restriction turns into this in TR space. And now we are at a stage where we can sort of mentally forget the tildes and just imagine that these are the T and R, the tildes. So this is R, which is really R tilde, and this is T, which is really T tilde. And now you can draw these constraints and mark the boundary. So T goes from minus pi here to pi. R goes from 0 here also to pi. And these, the second line gives me bounds that I'm inside this and I'm inside that. So the entire Minkowski space-time has been mapped into this. Now there's a little bit of a subtlety here. Supposing we were in real 1 plus 1D Minkowski space-time. In 1 plus 1D, R would not have been positive because I just have x and t, two coordinates. Okay, so in that case I should also have the left side over here. R would actually go from minus pi to pi for a pure 1 plus 1D system. Why don't I have that as soon as I go to 2 plus 1D? Because of the extra sphere, that D minus 2 sphere, which is extra over and above T and R. Let's look at it in 3D, 2 plus 1D. So there's only a circle there. That's a circle. And that tells me that there's a circle at every point here. So this, I imagine, is rotated like that. Okay. So automatically it includes the other side, but in fact a whole volume around. The only thing that's weird is that that circle shrinks to 0 here and here. And that's an artifact of our new metric, or conformally compactified metric. It's not a true property. We have actually scrunched up a lot of infinitely many true space-time points into a single point. Now let's label the points. This goes by the name of I plus. This one goes by the name of scry plus. I really don't know what scry is. I didn't even know there was such a symbol. And this goes under the name, goes by the name of scry. Minus, this point is called I minus, and this point is called I0. Now let's try to understand a few properties of this. There's also an equation which I didn't write down, but it's worth writing quickly. Just telling me how this T tildes and R tilde are related to T and R. So T tilde is tan, just to show you how nonlinear the transformation is. I could have skipped all the intervening steps and just said I'm making this miraculous transformation on my original metric. So, yeah, this is now I'm in a bit of trouble. I guess I have to say honestly that these are the tilde ones. Or are these the untilded ones? They're the tilde ones. Yes, of course, because they go between these ranges. Thank you. Okay, and similarly this minus tan inverse. This transformation, by the way, you can tell one nice thing about it immediately, just looking at it. Supposing, first thing is that if I add t plus r, I only get a function tan inverse of t plus r and the other one. But in fact, just looking at the equation for t alone, supposing my original thing was a light ray. For a light ray, either t is equal to r or t is equal to minus r. One of these terms is absent. I can also shift the light ray. It could be t equals r, could be t plus a constant. That doesn't matter. Then one of these terms is constant. Then the transformation is simple. It becomes not simple only if both terms are activated, which will happen if r is proportional to t, but the proportionality is less than 1. That's a time-like particle. Then both terms are there, and then things will change. And this is why light, the straight lines of light will remain straight lines, but the straight lines of massive objects will not remain straight. Okay, so let's, okay, we can also do one thing here. We can remember our coordinates u and v, and notice that u tilde is the coordinate that goes this way. And its value is minus pi by 2 here and pi by 2 here. While v tilde is the coordinate that goes this way and takes the value pi by 2 here and minus pi by 2 here. It's useful to remember that. Good. Okay. Now, trajectories. Okay, I already said this about the sphere. So we have to imagine a d minus 2-dimensional sphere at every point, which is largest here and shrinks to 0 on the vertical line. Often in books you will find that this vertical line is shaded like this because it's a singularity of the coordinate system. And the blame is just on our original choice of spherical polar coordinates. Okay. One exercise for you is that to understand why, for example, this point is just a point. This point actually ought to be, this point rather is just a point. This ought to be a whole volume, but space-time has got scrunched. So if you look at the conformal factor 2 cos or cos u v, which we multiplied the metric by to go to the compactification, you will see that that factor diverging is causing the space-time to collapse into a point. Okay, now for a light ray, we have the trajectory t is equal to plus or minus r minus c. So now let's ask, so the light ray is going to be at 45 degrees because of that equation. So it's going to be like this or like this. Now a line at 45 degrees inside this diagram, not at infinity, cannot reach these points, I plus and I minus. because it's strictly at 45 degrees. But if it's this way and I produce it back, it will reach here. If it's this way and I produce it forward, it will reach there. So therefore, light rays always start, and this is in the past, that's in the future. This comes from just the time. So light rays start from scry minus and end on scry plus. Now it's a bit weird to see how that happens. Let me erase some of this extra information, otherwise the diagram is becoming too busy to appreciate. So let my light ray start here. So this is fine, it's going inward. But at some point it hits the origin, and what is it going to do now? There is nothing here. But all this time it's been on a point of a circle or a sphere which is shrinking. But in real life that sphere is not shrinking. And so actually once it reaches here, it's going to get to the antipodal point of that. And so now once it hits here, it will bounce as it were and go there. So actually this trajectory is a single trajectory of light going from minus to plus infinity in real Minkowski spacetime. Okay, so there is always this bounce effect at the origin. The only case where the bounce is not there is 1 plus 1d, where there is a left side in the diagram, and then the light ray will smoothly go and hit this component of scry plus, which will be here. And there is no bounce, I'm just using that word. It's a bounce on the diagram. It's just smoothly going straight on a geodesic. These are all geodesics. We're just talking of a free light ray, and it's in flat space-time.
Sir,
Yes.
So you used antipodal points of a sphere. So there's a sphere at each point.
Yes.
So when the ray is starting at scry minus, then suppose goes to another point. So it's like jumping between the spheres.
It's not jumping between the spheres.
Ah.
My conformal compactification is making the sphere artificially shrink to 0 size. So I actually don't know what happens here.
Ah.
But I know that geometrically there is nothing here because it's an empty Minkowski space-time. So it has to pass through here. But once it passes through, it's so there's a artificial origin in my coordinates, and I have a ray which is hitting the origin. While it's approaching the origin, r is decreasing. Once it crosses the origin, r is increasing again. That's because I picked an origin. Okay, so I know that after it passes this, r must start increasing, so it must simply turn into that. Now this particular one I just happen to draw this way, but let's draw a light ray that starts way up here, then it will go all the way like that and then that. Or I can draw one here which will go here and then like that. So there are all these possibilities. Now that's a very interesting thing. Take a look at this point and this point. They are very different points because this is the initial point of a light ray which almost makes it to scry plus, while this is the final point of a light ray that almost started at scry minus. These are not at all nearly the same thing. They are completely different. These are not light rays which are near each other. To get from being this to being this, I would have to go the entire length of the v coordinate. Okay. Moreover, this is the initial point of this light ray, while that's the final point of this other light ray. And that's because this one is in the future and this one is in the past. There's a lesson here which actually people are still working on, which is that I0 should not be thought of as a single point. When I say single point, of course it has the sphere also, but even then it's not a single point. What I really mean, to be very precise, is that limit of, so there it was the u coordinate, as I recall on this. Yeah, the u coordinate. So limit as u coordinate goes to minus pi by 2. Okay, let's assign coordinates. What is the coordinate of this in uv? So v is this, so it's pi by 2, and u is minus pi by 2. So limit u goes to minus pi by 2 while v is at pi by 2 is not the same as the limit v goes to pi by 2 while u is at minus pi by 2. So here what is happening is we are approaching that point either from below or from above. Okay. In one case I am approaching this from above, u goes to minus pi by 2, so I come down that line. In this case I am approaching it from below, I go up that way. I've just argued for you that there are two light rays which really are not the same in any possible physical way. So we should, so this is important. Therefore I0, although it's a point in the Penrose diagram, it would be misleading to make too much out of that being a single point. It has two different, it corresponds to two different limits. That's one lesson. Okay. Now that's what we can say about light rays. We saw that they can get as close as we want to I plus or I minus, but not exactly touch, because if it's exactly here, it doesn't seem to have anywhere to go. On the other hand, massive particles are quite different, and it's a nice exercise to work out the trajectory which is obtained by solving that equation, because a massive particle in the original coordinates will have t equals plus or minus a constant. I don't want to call it alpha, well, I'll call it alpha, but it's nothing to do with acceleration. Okay, but alpha has to be greater than 1 for it to be time-like. And so you just try to put this into that equation and then follow the equation for t going to plus infinity and t going to minus infinity, future and past. And what you find is that these massive particles actually don't go on straight lines, even though the geodesics are actually straight lines in the TR coordinates, but in these coordinates they go like this. Okay, so this is massive, or time-like trajectory if you like, the same thing. So all massive particles start at the same point I minus and end at the same point I plus, and they just probe the interior of this space-time while they're traveling. So if I, for example, if I was a massive particle sitting here at the origin of this time, I don't have to do anything. Of course, in old coordinates, I'll go vertically. That's being at rest. But in these coordinates, my trajectory will bend until it goes to I plus. Yeah, question?
Yeah, coming back to the massless case.
Yeah.
So another way of phrasing what you just said, that I naught should not be thought of as a single point, is maybe saying that you take Maxwell's equations and you want to set up boundary conditions. You have to do it both at I0, a small neighborhood on scribe plus a small neighborhood.
Very good. Yes.
And these are all independent data that you have to specify.
Yes.
So,
Good. I think that's absolutely right. And actually, there's some research in recent times. I think Subrat Raju even has a paper on this on the nature of I0. Before that, I think many years ago, I think people like Ashtekar and so on have also worked on it in the context of gravity. You brought up a very good point, actually. The only other massless or light-like thing we have in nature is the photon and electromagnetism, and a lot more is known about it because it's a much older subject. So Wald, for example, at many points in his book, you find nice analogies he points out between some equations here and some equations from Maxwell's electromagnetism, or some physical behavior of trajectories and so on. And especially since we are here in Minkowski spacetime, that is the setting for Maxwell's equations anyway. So yes, so that's a good way to think about things. And I think I've said all. Okay. Yeah. Yeah, I have said everything I want to say. Any more questions? So this is only the Penrose diagram for Minkowski spacetime, and as I said, it will look different. If there's a black hole inside this spacetime, that is, which is asymptotically flat, it will look different. If it's ADS, it's very different. If it's DS, it's very different. And next time we'll do ADS and DS Penrose diagrams. Okay.